Okay, last time we were talking about chapter 14 steel, and we got into weak bases. And again, weak bases basically work the same way as weak acids, except that obviously you have a KB type situation happening. Also, for example, we looked at, I think, ammonia, and when ammonia reacts with water, it's going to accept the H plus there, and that's going to make NH4 plus and hydroxide here. So when we do our ice table and we do solve for X, a reminder that it is hydroxide that X equals. And again, that will give you the POH, and then you could get to the pH. So very similar to how you do sort of weak acid problems. Again, you can make an assumption if it works. But you do get the hydroxide, which will get you, like I said, the POH first and then to the pH. Then we talked about salts, and salts are really derived from acids and bases. So the reaction of an acid and a base will usually make a salt in water. And really, the important part of the salt is where it came from in terms of what type of acid or base it is. A reminder again, that sort of opposite relationship, and that is if it is a weak acid or a weak base, then this salt will go through hydrolysis. So its conjugate partner will go through hydrolysis because it came from a weak acid or a weak base. If it comes from a strong acid or a strong base, which for our strong bases, usually that means that it comes from somebody from group 1 or 2 on the periodic table, it will not go through hydrolysis and react with water. And that would give you a pH of 7 for those guys. If it does react with water, it will react in one of two ways. Either the salt component, the ion, will, when it reacts with water, either take the H plus. The result of that is you will form OH minus on the product side, which means its solution should be basic. The other option is the salt ion can donate over to the water in this hydrolysis reaction. That will produce you your H3O plus, which means the solution should be acidic. As we talked about, these are very common problems, these hydrolysis type problems, where they sort of give you the wrong K value. In this case, remember that if you ever see hydroxide on the product side, that is basic, which means you should be using the Kb value. If you see H plus or H3O plus on the product side, that means you definitely should be using a Ka value. And you could go between those two by using Kw, which is Ka times the Kb. And again, Kw is our 1 times 10 to the minus 14. Questions on any of that there? All right, so I think we did an example there. So I think we might be on this example. So why don't you give this a go? We want the pH of this 0.75 sodium cyanide solution. The Ka for HCN is 6.2 times 10 to the minus 10. A salt here, and again, when you do have a salt, you want to think about what two sort of ions come from that salt. In this case, we have a sodium ion because it's a strong electrolyte. Bless you, it should completely break apart into sodium and cyanide. So once you do that, what you want to then analyze really is both parts here of the salt and see if any of it will go through hydrolysis. Sodium, which is group 1, will not go through hydrolysis because really it comes from sodium hydroxide. So we don't have to worry about that. That's basically a neutral salt. It won't react with water. The cyanide here comes from here, HCN, which was given to us in the problem. And since HCN is a Ka value, that tells me that this is a weak acid, which means this guy would be its conjugate base, and it would go through hydrolysis again because it's a weak acid. So that is the reaction we're going to have. We're going to have the CN minus is going to react with water through this hydrolysis reaction. Again, by understanding that it comes from this weak acid, we can understand that it is acting as a base when it reacts with water. And that means that it will accept the H plus. Again, by the fact that it doesn't have an H, it can't give it if it wanted to. So it could only really accept here. The result of that is, as I mentioned the other day, you always get back pretty much where that salt came from. So that salt came from here, which by the way is right there. So you probably have your reaction that you need to write, and that is hydroxide here. So once again, we should know before we do the calculation that this solution should be basic because we're producing hydroxide in this case. And now we could do an ice table. And again, since this guy is 0.75 molar, it is a 1-to-1 relationship between those two. And that would mean that the cyanide is also 0.75 molar. We'll go with our zeros here, our change minus x plus x plus x. Equilibrium 0.75 minus x, x, and x. This will go into our K expression here, and that's going to be our products, which is HCN, OH minus, and a little bit of CN minus there. This, though, should be a KB, right? And again, it should be a KB because we have hydroxide here. So we do not want to use the Ka value. Super common in these problems. They again give you kind of the wrong K value, if you will. So we do need to use Kw there to convert it. So our Kb would be our Kw divided by the Ka value. So that's going to be 1 times 10 to the minus 14 divided by 6.2 times 10 to the minus 10. And that's going to get us here. I don't know. Let's see. It's going to get us 1.6 times 10 to the minus 5. So putting in our values would get us x squared divided by 0.75 minus x equals 1.6 times 10 to the minus 5. We could assume x is equal to 0. That's going to get us x squared divided by 0.75 equals 1.6 times 10 to the minus 5. Once again, we're going to divide, and then we're going to square root. And we do that, we will not divide. I'm sorry, we're going to multiply. We're going to multiply and then divide and then square root. I'll get that right. So we're going to multiply and then square root it. There we go. And then we're going to square root. And that is going to get us basically an x value of, looks like an x value of 0.00001606. We do need to check it, so we'll divide that by 0.75, times it by 100%. And I think we should be in good shape at that point. We're not even 0.1%, so the check here is good. First off, any questions so far on that calculation? Now that our x value is good, we again could go back to our table. And again, like I said earlier, we do see in this case that the x value actually is the hydroxide concentration. So our hydroxide concentration is going to equal my number I had there, which is something here, right there, I think. There are a little scientific notation, so not so much to write 1.606 times 10 to the minus 5 molar. That's going to go into our POH equals minus the log of that there. So minus the log of that going to get us a 4.79. That is our POH. So again, our pH here, we find an open spot right there. 14 minus 4.79. And that will give us the actual pH here of 9.21, it looks like. Yeah. This particular case. That is basic, which hopefully it does make sense. Again, since we are producing hydroxide, so we would expect the pH here to be basic. Any questions on that there? So salts, again, the key is to determine, obviously, like I said, what if it will go through hydrolysis. If it will not, again, it's going to be a pH of 7. But if it is, you do need to do some type of ice table and solve for it. Obviously, if we have an acidic salt, works the same way, except that once you get to the X, that is the H plus concentration. So you could go directly into the pH. You don't have to, obviously, do the 14. Any questions on salts there? So what happens though if you did have a salt that perhaps this way here, that both parts could go through hydrolysis. So for example, let's say you had ammonium nitrite, and ammonium nitrite would break apart into the ammonium ion and the nitrite ion. And this salt most likely came from ammonia reacting with nitrous acid, not nitric acid, but nitrous acid. And again, here that would produce our NH4 plus and our NO2 minus. That is a weak base, which means this right here is its conjugate acid, and it will go through hydrolysis. That is a weak acid, and that would be its conjugate base here, which means it will also go through hydrolysis as well. So although a lot of times when you do come across a salt, maybe only one part of the salt will go through hydrolysis, it is possible that you could create a salt where actually both of them would go through hydrolysis. Now, obviously, the calculation would be pretty complicated since you have two salts going through hydrolysis at the same time, and really one would produce H plus and one would produce hydroxide. So in a situation like this, where you actually do come across perhaps a salt where both parts will go through hydrolysis, what we actually do is compare the Ka value to the Kb value. So we compare the Kb value for the anion to the Ka value for the cation, the positive guy. And if you do that and the Kb value is bigger than the Ka value, then you could assume that the solution would be basic, and you basically would do a Kb problem. Now, if you look at it and the Ka value for the positive guy is larger than the Kb value for the negative guy, because Ka is larger, you would assume the solution's acidic, and you would do a Ka type of problem in that case. And if the Kb value is approximately the same as the Ka value, then you could assume that it is going to be neutral, and obviously a pH of 7 in that particular case. So in a situation where we can have both salts going through hydrolysis, or both parts of the salt going through to hydrolysis, you compare the Ka to the Kb value. Again, whichever one is larger, essentially you'll just assume that's what's going to happen, and you'll just do that problem. You'll ignore the other salt part of the salt. Any questions on that there? All right, it's a little table that kind of summarizes some of the stuff we talked about there. Obviously, no hydrolysis, pH is 7, anion goes through it. We're going to have less than 7 and greater than 7. If the cation goes through it, again, comparison here if necessary. So let's talk a little bit about oxides. Oxides are elements that obviously have oxygen in them, and oxides can create either acids or bases when they react with water. So for example, a lot of our basic oxides, probably no surprise, can be found here in group 1 and group 2 on the periodic table. Again, this is where we get things pretty much like sodium hydroxide, potassium hydroxide, calcium hydroxide, strontium hydroxide. And again, these oxides will basically produce bases when they react with water. Over here, sort of in the nonmetal region of the periodic table, these guys will have oxygen, and when they react with water, for example, if you took some water and some CO2, it'll make some carbonic acid. These are our acidic uh, oxides over here on the right-hand side. Those guys typically, when they react with water, will produce acids. And then obviously we have a few orangey guys here, and those are amphoteric. And as we talked about, amphoteric substances are ones that can really go either way. They can basically make an acid or a base, kind of depending on the situation that occurs. So as we sort of think about it, really our bases come from the left-hand side of the periodic table. Really our acids there come from the right-hand side of the periodic table. And that's where we get most of these guys from. Now, We talked about a couple of definitions of an acid and a base. We have the Arrhenius definition, which is again an acid that produces or has the ability to produce H plus in solution. A Bronsted-Lowry definition of an acid is a proton donor. So why not have Lewis? And Lewis acid and bases are also a definition of an acid and base. And when we think about Lewis, we think about Lewis structures. And when we draw Lewis structures, you involve electrons. Yeah, and that's what you draw. So probably no surprise, a Lewis acid and base actually involves electrons and not protons, but involves electrons. And a Lewis acid is something that will accept a pair of electrons, while a Lewis base, which we'll see in a number of places throughout some of these chapters, a Lewis base is something that will actually donate a pair of electrons. So the Lewis definition of acid and base is one that involves electrons, and electrons being donated and electrons being accepted. Now, when we think about, what would make something a good Lewis acid, something that would want to accept electrons, that is something that is frankly electron deficient. And what that means is essentially, if you are losing some electrons, you become positively charged. So things that are positively charged are usually really good Lewis acids. That's why a lot of complex ions have a highly positive charged metal in the middle. They've lost a lot of electrons, allows them to accept electrons from these ligands that come in and attach to them. Also, things that do something like boron, which is an incomplete octet, has places for those electrons is electron deficient. Things that are good Lewis bases are things, for example, that are negatively charged, like chloride. It has a negative charge because it gained electrons, which means it has electrons to donate. Things that are polar and also have non-bonding electrons, like water is a really good Lewis base. Ammonia, which also has non-bonding electrons and is polar, is a really good Lewis base as well. So here in this definition here, as we can see, we have our hydroxide donating a pair of electrons to the hydrogen ion because it's positively charged, it's missing electrons, so it's willing to accept it, making this our Lewis acid and this guy our Lewis base, right? This is ammonia, which is polar, has the non-bonding electrons on the nitrogen, allowing it to donate over there to our hydrogen in this case, again, making the hydrogen our Lewis acid. And this guy here would be our Lewis base in this case. Now, do you end up with the same sort of acid-base definition as you do with Bronsted-Lowry and others? The answer is yeah, you still do, because if we were looking at this, both of these in terms of Bronsted-Lowry, this guy would be donating its H plus over, which would make it an acid, and he would accept the H plus, which would make it a base. So you still get the same acid base sort of definition. Same thing here. This guy would donate its H plus over, and that would make it its Bronsted acid. The NH3 would accept the H plus, which would make it the Bronsted base. So when you have an H plus involved, it's still really the same definition. You could look at it as a Bronsted-Lowry definition. You could also look at it as a Lewis acid-based sort of definition as well. The benefit of sort of the Lewis acid definition is that you actually do not need a proton to be involved to sort of describe something in terms of acid and bases. Here we have no proton involved, but we do have boron, which is an incomplete octet, which means it has less than 8 electrons around it. That makes it pretty primed to accept, again, our electrons over here from our NH3, making this our Lewis base and this our Lewis acid. Here, no proton is involved, right? So no H plus being transferred, but we could still apply basically acid-base chemistry to this. Something that we'll talk about later on is complex ions, and that's essentially how we look at complex ion formation is more of a Lewis acid base, electrons being accepted, electrons being donated, rather than other sort of interactions that occur. Any questions on Lewis acids and bases there? All right, so let's then talk about polyprotic acids. Polyprotic acids are obviously acids that have more than one hydrogen to give. So again, as we talked about, I think earlier on, you can have HA, which is monoprotic. It's basically got one hydrogen to give. H2A, which is diprotic. It's got two hydrogens to give. And H3A, triprotic, has three hydrogens basically to give. Each of those hydrogens actually do come off basically one at a time. So for example, if we took a look at phosphoric acid, the first thing that would happen with phosphoric acid is it would lose an H plus and basically become H2PO4 minus. That equilibrium would have an equilibrium constant associated with it, which is known as the Ka1 value here in the table. The next thing that would happen is this H2PO4 minus would then dump off one more hydrogen. And that would make HPO4 2 minus, becoming one more negative. And that also is an equilibrium that has a Ka value within. That's known as the Ka2 value that you would see in the table for phosphoric acid here. And lastly here, this guy would then lose one more hydrogen and make phosphate in this case. And that would be our Ka3. So if we just grab some of these numbers here off of this table here, we can see we got 7.5 times 10 to the minus 3 for the first one, 6.2 times 10 to the minus 8, and 4.8 times 10 to the minus 13 there for our last one. Now, what we see is it easier to take off the first hydrogen or the second? Which one is easier? The easiest one to take off is the first one, yeah? After you take off the first one, you then become something negatively charged. So you're trying to rip off a positive proton, so that makes it a little harder. And then it gets even harder as you try to rip off that third one, right? Because now you got something that's -2 charge, right? And trying to rip off something that's positive. So it's going to be a little bit harder. We actually see that reflected in the K values. First K1 value here is to -3. Then it gets much smaller on the second hydrogen coming off, which means we mainly have reactants. Then it gets even smaller as you get to the third one, which means you pretty much mainly have reactants. Not a lot of it is coming off in this case. So it does get progressively harder every time you kind of take off a hydrogen along the way. Any questions on that there? So we'll come back to this, I think. Let's take a look at a problem that we might want to do here to calculate a bunch of things. We want to calculate the concentration of pH, or the pH of H3PO4, H2PO4 minus, HPO42 minus, PO43 minus, and H plus of a 5 molar solution. So in this case, we actually want to calculate the concentration pretty much of everybody involved in this equilibrium. And if we look back at sort of our equations I just had there, that pretty much is going to mean we're going to have to go through each of these equilibrium steps to basically find the concentrations of everybody. So let us do this one here and see how we work this. So obviously the first thing that's going to happen here is got 7.5 minus 3. So we're going to have our H3PO4. It's going to break apart into H plus and H2PO4 minus. And that's going to give us our Ka1 value that we saw there, which was our, we got there, 7.5 to the minus 3. So we're going to start with our initial concentration of our acid, which was 5 molar in this case. We're going to do a regular ice table here. So 0, 0. Change is going to be minus x plus x plus x. That means at equilibrium, 5 minus x, x, and x. So we're just going to do a regular old sort of ice table here to figure out what's going on. This would go into our Ka1 expression, which is our products over our reactants. That would essentially give me x squared divided by 5 minus x equals 7.5 times 10 to the minus 3. We're going to assume that x is equal to 0 here, and that's going to give us x squared divided by 5 is equal to 7.5 times 10 to the minus 3. Once again, we're going to multiply and then square root it. And that's going to get us here 7.5 to the minus 3 times 5, a little square rootage. And that's going to give us an x value here of 0.194. We do want to check it. We'll divide it by 5, times it by 100. And we are at like 3.9%, which means the check here is good, which is probably why I changed it from the original problem where it wasn't good. But here I did that, so that we're good. So after this first table, we do have a few of the answers that we're looking for. We could clearly see after the first table here, the concentration of H2PO4 minus equals X, which means its concentration would be 0.194 molar. We could also see the H plus concentration here equals X. So the H plus concentration equals 0.194 molar. We could also see that our phosphoric acid's concentration is equal to 5 minus X, which means H3PO4 would equal our 5 minus our X there. And that's going to get us, and we'll call it 4.81 molar. So off of this first ice table, we were able to really kind of figure out 3 of the concentrations we're looking for. So we're able to get basically this guy, we got that guy, and we got that guy's concentration. Now we're interested in this guy's concentration, and that guy only shows up, I believe, pretty much in a couple of places. So we will have to go to the next step here to get the rest of the concentrations. So that is our Ka2. So let's take a look at what's happening here. So what's going to happen is coming from our first ice table and our first hydrogen coming off, that guy is then going to lose another hydrogen. So we're going to rip off the next hydrogen here. And that's going to leave us HPO4 2 minus. And that's going to be our Ka2, which was 6.2 times 10 to the minus 8. Now, important when we do this, if we go back to the previous table, we actually do have some initial concentrations of these guys that's in our second table. So our equilibrium concentration of H2PO4, which was this, is what our initial concentration is going to be on this table as we're continuing on. So that's the initial concentration. Also, not to be overlooked is from that previous table, we also had H plus that's now in dissolution. So we should have an initial concentration of our H plus as well. So again, those 2 initial concentrations come from the equilibrium line. This is going to be 0. Rest of the table going to be very similar, minus x plus x plus x. This is going to get us 0.194 minus x, 0.194 plus x, and x. Any questions on the table? So because this is a stepwise association, we actually do have some initial concentrations that essentially come from the final or equilibrium concentrations of sort of the previous hydrogen coming off. This is going to go into our Ka2 expression here. And putting that in is going to get us 0.194 plus x times x divided by 0.194 minus x equals 6.2 times 10 to the minus 8. We did the assumption on the first one and it worked out pretty good, so why not give it a go again? We're going to assume x is equal to 0. In this case, we're going to get rid of the x's we're adding or subtracting from a number. That's going to give me 0.194 times x divided by 0.194 equals 6.2 times 10 to the minus 8. I think I could do that math. That is that. So x is equal to 6.2 times 10 to the minus 8. We should check it. So if we divide that number there by 0.194 and times it by 100, the check is good in this case. So what does that give us now? If we go to our ICE table, we can see that in this case, the X value equals the concentration of HPO4 2 minus. And in this case, it would equal 6.2 times 10 to the minus 8. Now, what happens in this case when I take my X value here and I put it into here and here? Does the number change? If you take 0.194 and you subtract 6.2 times 10 to the minus 8, you still get 0.194. It doesn't change, yeah? And the same thing, if you added it, it still stays basically the same. You could do it if you don't trust me, but it will become the same. So very small amount, right, coming off in this case. So now we're pretty close to what we want. We now have this guy's concentration. That means really the last one that we're looking for is the phosphate. And the phosphate does reside here in our third hydrogen that comes off. So we will need to kind of do our third step here to get to the phosphate. And let's do that one then. So continuing on here, the next thing that's going to happen is this guy that has already lost 2 hydrogens will now lose a third one in this case. And that will make the phosphate that we're looking for in terms of the concentration. This is going to be our Ka3, which is 4.8 times 10 to the minus 13. Just like we did in the previous step, at this step in the game, we do have some equilibrium concentrations still there from the previous step. So we do want to use that. So our equilibrium of HPO4 2 minus was 6.2 times 10 to the minus 8. Again, coming from the equilibrium line of the previous ice table. We also still need to remember there is still H plus floating around, really, from the first one and the second one. And as we saw, the concentration after the second one is still 0.194. So we got that to open up with as well. And now we have 0. Any questions on that there? Change going to be normal, minus x, plus x, plus x. That's going to get us here 6.2 times 10 to the minus 8 minus x, 0.194 plus x, and x. This is going to go into our Ka3 reaction here, our H plus, our phosphate, and our HPO4 2 minus. Popping those numbers in, 0.194 plus x times x divided by 6.2 times 10 to the minus 8 minus x. And that's going to equal our Ka3 value there to the minus 13. Once again, we're going to assume x is equal to 0. Again, getting rid of the ones we're adding and subtracting from gives us 0.194 times x divided by 6.2 times 10 to the minus 8 equals 4.8 times 10 to the 13 negative. We're going to multiply and then divide what's on top there. So times 6.2 to the minus 8 divided by 0.194 gonna get me an X value here of 1.5 times 10 to the minus 19. Again, we could check it by doing either of those numbers, and neither one is anywhere near problematic, so that check is good here. At this point, that does give us really the reason we needed to come back this far to this step, the phosphates concentration, which is 1.5 times 10 to the minus 19 molar in this case. Once again, when we take this X value and put it back into each of these locations, do the numbers change? They do not. Again, if you took 0.194 and you added 1.5 times 10 to the minus 19, it'll still be the same. And same thing if you took 6.2 times 10 to the minus 8 and subtracted 1.5 times 10 to the minus 19, it would still be the same. That means that when we look at this, we see with numbers here exactly what we were talking about in terms of how hard it gets to remove hydrogens after you take one off. We see that the majority of all of the H plus that came off in which step? Came off in the very first step, right? The very first step when that first hydrogen came off gave us 0.194 molar. How much did we get off in the second step? Well, frankly, that's what we got off in the second step, 6.2 times 10 to the minus 8. Not very much, right? We didn't lose very much. We then, on the third one, got even harder. We basically got off that much hydrogen, right? Barely nothing came off. So the majority of the hydrogen actually comes off on the very first one. As you can see, it gets progressively really, really harder to remove that. So what that means is if you come across a polyprotic sort of acid problem, and the only thing that they basically want you to answer is what is the pH, basically. You basically don't have to do all three tables. You could pretty much just do the first ice table, and you could use the H plus concentration, and you could get the pH from that. Now, if you have a problem like the one we did in this particular example, which they wanted the concentration of everybody, then it may require you to go to like the second step and the third step like we did here. We should probably do also that part of the question, which was what is the pH? So we know that basically the pH here is minus the log 0.194, and that's going to get us a pH of 0.71, which I would say was acidic, yes. Any questions on polyprotic acid? So as we were talking about there, again, a majority of all of the H plus essentially will come off in that very first step. And you can, again, just basically use that to calculate the pH if that's all you're looking for. All right. There you go. All right. Any questions on that there? That completes part 1 of chapter 14. We are going to go off to part 2 next. On to, we'll call it part 2. Part 2 of chapter 14, which is, I would say, the hardest part, perhaps. We are now getting into perhaps the hardest part of the course for a lot of people, or the difficult part of the course for a lot of people. Here we're going to talk about buffers. We're going to talk about titrations, which the good news is it's really a lot of the calculations that you've already done. The hardest part for a lot of people is to the understanding conceptual part of it, of what's going on in the problem, so that you do the correct math. So that's really the key part here. So let's get into this. And the first thing we're going to really talk about is something, there it is. We're going to talk about the common ion effect. Now, the idea of the common ion effect is it will shift the equilibrium away from the common ion, and the presence of a common ion will essentially keep a weak acid or weak base together. It will prevent it from ionizing or dissociating because of the presence of the common ion. So what do we mean by that? Let's just take everybody's favorite example, which is acetic acid. And if we take acetic acid, which is like what we find in vinegar, it is a weak acid. And by the way, I know it's a weak acid because it's not one of the 6 strong acids that we talked about. So I do know for sure it's a weak acid. And it will dissociate into acetate and H plus in this case. Now, this is going to be sort of its normal dissociation that's going to occur. Now, if you took, for example, acetic acid and you just put it into the beaker, that's essentially what you got going on in that beaker, arrows and all, I suppose. You got basically these guys kind of floating around. Now, if you took that beaker and in addition to the acetic acid, you decided that you wanted to put in there perhaps a salt like sodium acetate. And because this is a salt, it will be a strong electrolyte and will 100% break apart into sodium ions and acetate ions. So basically, these two guys are now going to go basically for a swim into here. And when they go for a swim into the pool, hopefully you can see in this case, we have now added more acetate. That is our common ion, basically. So we basically added more acetate here. And when we do that, based on Le Chatelier's principle, which is if I added more acetate, which way should the equilibrium shift in this case? It should shift away from the side you added it to, so it should cause the equilibrium to shift to the left in this case, right? And it's going to cause this equilibrium when you do that. You're going to have a lot more of this, which means you have a lot more products in your beaker, and that's going to cause the equilibrium to shift to make acetic acid. When it does that, the consequence in terms of pH is what happens to the H plus concentration? It goes up or down? It would start to go down, right? And that's because the reverse reaction is happening. In order to make that reverse reaction happen, you need both of those guys to come together. So we would actually start to see a decrease in the concentration of H plus because of the common ion. That means because H plus and OH minus are tied to each other, we would actually see an increase in the hydroxide concentration. And that means that our pH would actually go up. Yeah. Will it go up to basic? No, probably. But it would be higher the pH than it would be with the acid by itself, right? With the acid by itself, it's going to be able to release a certain amount of H plus, but with the common ion being present, it's going to keep it together and not allow it to release as much. And you would see a higher pH value because of that. Any questions on that there? A base works the same way. If you have a common ion with a base, basically it's going to force the base back together, which means it's going to prevent less OH minus being in the solution. And less OH minus in the solution means that you will actually have a little bit more H plus, and you would actually see the pH in the common ion less than where it started at because it has less OH minus in the solution. Any questions on that there? All right, there. So let's take a look at a couple of these here. We'll start with the first one. Calculate the pH of a 0.2 molar acetic acid solution. So just start with that. Just part A, Ka value here, 1.8. All right, so let's take a look at part A. So part A, we have 0.2 molar acetic acid. We have the Ka value given to us. So really for part A, this is just a weak acid problem. So that acetic acid is going to set up an equilibrium. We'll acetate and some H plus here. Then we have a Ka value there, 1.8 times 10 to the minus 5. So initially we have 0.200 change minus x plus x plus x and equilibrium here, 0.2 minus x, x and x. So really just a basic sort of Ka type of problem like we've done previously. This should go into our Ka expression, which again is our products divided by our reactants. Putting in there x squared 0.2 minus x equals 1.8 times 10 to the minus 5. We're going to assume x is equal to 0 here, so that will get rid of this x. That will give us x squared divided by 0.2 equals 1.8 times 10 to the minus 5. We're going to multiply and then square root. So that will get us 1.8 to the minus 5 times 0.2, a little square rootage. Going to give us an x value here, 0.001897. We do want to check it, so we'll divide by 0.2 times it by 100. I think we're going to be okay, I think. It's like 0.9%. So the check is good in this case. That's important because here, obviously, we're looking for our H plus concentration. So that would equal our H plus concentration, which is equal to X. And that is 0.001897. That then could go right into our pH to give us an opening pH here of 2.72, I think. Yeah, if I'm not mistaken. 0.001897. 2.72 it is. Any questions on any of those steps there? So this again is just a basic sort of weak acid problem. So let's take a look at part B. In part B, we're going to take the same acetic acid, but in this case, we're going to dump in there 0.3 molar sodium acetate in there with it. So let's take a look and see what's happening in this deal. So we will have into our beaker our acetic acid. And that acetic acid, when it goes in, will set up the equilibrium. So that is the only thing that's going to really kind of set up the equilibrium there in our solution. When we take our sodium acetate, that is a strong electrolyte salt that will break apart completely into sodium ions and acetate ions in this case. So that is going to go in here to the beaker. So out of the two, again, it's just the acetic acid here that will set up the equilibrium. So that is what we want to do our ice table based off of. It is still the same Ka value that we used previously for acetic acids. It's the same thing. Initially here, we will have our 0.2 molar. We will have 0. But now because we are dumping in that sodium acetate in this case, and we know it is 0.3 molar. It is a 1-to-1 relationship between that and the acetate, which means we do have an initial amount of acetate being supplied by the acetate or the sodium acetate, and we do need to have an initial concentration over here. Again, this is being supplied by that sodium acetate that we are dumping in there. Any questions on that? Probably the most missed type of situation when people do these type of problems is they're so used to putting zeros on the right-hand side that they just zero out the right-hand side at this point. What would happen if I did zero out the right-hand side? I'm basically doing the exact same problem I did for part 1, right? Or part A, right? So we don't want to do that. So because we have this common ion, we got to have an initial concentration on the right-hand side of that common ion, and that's obviously going to affect some things. So let's see how it affects some things. The rest of the table is really going to be the same, minus x plus x plus x. We are going to go 0.2 minus x, x. Next thing that people screw up on is right about here because they're used to minusing x's. So remember, that's a plus x, not a minus x in this particular case. This is going to go into our Ka expression for our weak acid, which is our acetic acid like normal here. And putting it in there gives us x 0.3 plus x divided by 0.2 minus x equals 1.8 times 10 to the minus 5. Might as well assume that x is equal to 0 here. We've had pretty good luck. So once again, we're going to get rid of these x's here. We're subtracting or adding. That will get us x times 0.3 divided by 0.2 equals 1.8 times 10 to the minus 5. Again, we're going to multiply and then divide the 0.3 to the other side. We'll go 1.8 to the minus 5 times 0.2 divided by 0.3. Gonna give us an x value in this case. Too many zeros here. X is equal to 1.2 times 10 to the minus 5. We'll check it by dividing by 0.3, timesing by 100. And I think again here we should be in good shape. And we are, so the check is good. That means in this case, once again, going back to our table, we could see that x is equal to the H plus. So that would be basically our H plus concentration. And that means that we could calculate our pH, which is minus the log of 1.2 times 10 to the minus 5. And that is going to get us a pH here of 4.92. First off, any questions on that calculation there? Again, the key here is, like I mentioned before, that initial part there and making sure that you are adding here. Now, did we see what we expected to happen here because of the presence of that common ion? Well, we have a pH without the common ion of 2.72, right? We also have an H plus concentration of 0.0018. With the presence of the common ion, our pH actually goes up and our H plus concentration goes down, which is what we would expect to happen because once again, with the presence of this common ion, Le Chatelier's principle is going to push the equilibrium back that way. The result of that is the H plus concentration should go down. The pH here should go up. And that is what we see here in this case with our numbers. Any questions on that there? Okay. Now, in problems like this where you have common ion, we usually get starting concentrations that are not too small. So as long as you have sort of okay concentrations of your acid and base, the initial concentrations usually end up being the final concentrations. So if you take a look at like here, if we took our 0.2 and our 0.3 and added or subtracted our x value, which is what we would do at equilibrium, we essentially would still have 0.3 and 0.2. Concentration didn't change all that much from beginning to end. So in situations like this, you do actually have an alternative to doing an ice table. And you could use what is referred to and derived there on the screen as the Henderson-Hasselbalch equation. The Henderson-Hasselbalch equation is the pH is equal to the pKa plus the log of the concentration of the base divided by the concentration of the acid. The pKa is minus the log of the Ka value. This is pretty much the formula, as we will talk about shortly, that we use for buffers. This is pretty much your equation to use for buffers. Now, the Henderson-Hasselbalch equation can also be written for POH, and you could have a POH version of that, which is the POH is equal to the pKb plus the log of the acid concentration over the base. pKb in this case would equal negative log of the Kb value. So this is also another version of it, but in my opinion, I wouldn't use it because probably most of the time you're looking for pH. So why not just use the equation that's going to give you the answer you need? So you could use the Henderson-Hasselbalch equation with pH for acidic conditions, basic conditions, neutral, it doesn't matter. So you might as well just, in most cases, just go into here and use it. But what happens if you are given sort of basic information? The reason this is an okay thing is because if you take the pKa value and you take the pKb value and add them together, you get 14, which means if maybe you're given a Kb value and you want to use this equation, you could get the pKb value and then subtract 14 and you'll have the pKa, and then you could go into the equation, the pH equation, and get it and stuff like that. So sometimes you will see people use this one in sort of basic conditions, but again, in my opinion, since most of the time you're looking for pH, you might as well just go into the Henderson-Hasselbalch equation, not worry about it. So with that being said, if we think about what we had previously, which was 0.2 molar acetic acid and 0.3 molar sodium acetate in that last example, and a Ka value of 1.8 times 10 to the minus 5. So, by the way, these two things are related to each other, right? If I get rid of the sodium here, these guys are definitely related to each other, right? They are Bronsted-Lowry acid-base combination, right? We have a weak acid and its conjugate base, basically. So that is our acid and its conjugate base, right? And that is always the situation, which is a common ion situation and also a buffer situation we'll talk about, that you want to use the Henderson-Hasselbalch equation. So if you could recognize that they are related to each other, basically by that difference of 1H plus, just like in Bronsted-Lowry, you could go right into your Henderson-Hasselbalch, David Hasselhoff, whichever equation you want to use there. We could do our pKa is equal to minus the log of the Ka. So minus the log of 1.8 times 10 to the minus 5, going to give us a 4.74 pKa. That means that the pH here is equal to 4.74 plus the log. Now, which one's my base? It is this one, right? The acid should usually have, by the way, one more hydrogen, right? So we could donate it, right? And usually a lot of times the base will have some type of spectator ion in there, like a sodium or something like that. So we want to go 0.3 up on top over our acid, which is 0.2. That's a 4.92. Yeah. And I believe that should be, what we got on that previous example there. 4.92, no ice table needed. Yeah, so that's not too bad. Question on that. So you can use this in only a specific situation, which is a common ion situation, and that is also mainly a buffer situation. You should not use this equation in every calculation unless you like to get it all wrong all the time, yeah? And that is a very big problem. People get two numbers and go, cool, I finally have an equation. I want to throw it into that equation all the time. You should only use this really in a buffer situation, which is really a common ion situation. That's the only time you should use it. But it does give you options. If you don't even want to worry about using it, you could still do the ice table. You just got to make sure you have the initial concentration on both sides, so you do the correct sort of calculation. If you could recognize that it is this type of situation, you could avoid the ice table and go directly into here and use it. Any questions on that